Hello, everyone. I'm Yogesh Jaluria from Rutgers University in New Jersey, and I have the pleasure of presenting this paper, uh, which has been largely done by my student, Xiaobing Zhang. The title is Constrained Optimization of Microchannel Cooling Systems with and Without Uncertainty. The focus is really on optimization and on uncertainty. We'll talk about it as we go along. The basic figure that you see here, which is Moore's law, is well known, that with time, the requirements for heat flux removal have been increasing, and we are fairly high now with several kilowatts per centimeter square as the heat flux to be removed. Uh, this is also well known that with macro cooling, with large channels, the heat transfer that can be uh, achieved is much less than what can be achieved with micro channel cooling, predominantly because of the Nusselt numbers that arises, as shown in this slide. These are just many microchannels, 10, 20, 25, 50 microchannels on a small area, which is about a centimeter by a centimeter. So the channels are basically of the order of 100 microns or less in most cases in width. They could be square, could be circular, and of course, there's a lot of conjugate heat transfer going on. This shows the dependence of pressure drop on channel width. As the channel width decreases, which you can see here, the pressure obviously increases, and at times it becomes critical to make sure that the pressure is within reasonable limits. But as I mentioned, the Nusselt number depends very much on the diameter or width of the channel. And if the channels are very thin, very small in diameter, you end up with a much higher heat transfer coefficient. And that's the whole idea behind using microchannels. The mathematical modeling is fairly simple when you're dealing with water or a liquid, because you can still use the no-slip conditions. And the basic equations are very similar, except that you do need much finer mesh sizes. And you also have to worry about viscous dissipation, pressure increase, and so on, pressure drop in the channel. So many of those things come in, but if it were air or nitrogen, we would be dealing with slip at the wall, and we'll be dealing with the temperature jump. But with the liquid, which we are considering here, that's not the case. It's a much simpler solution with respect to the heat and mass transfer in the flow. The basic model is a single channel, which you see here. And this single channel, many points have been chosen on this, largely to look for the hotspot, where the hotspot occurs, what the value is, and so on. And you can have a grid which can be made to solve for the single channel. And all these single channels that you see here, 40, 50, or 100, they're all basically combined to get the device. The device, as I mentioned, is about a centimeter by a centimeter, uniform heat flux condition at the bottom. And then, of course, you have either a PDMS or some other form at the top to cover the flow that is going on. So with this simple model, which, as you can see, is a square or a rectangular channel, we can solve the problem by using any of the standard CFD computational heat transfer models. So we did that using a computational heat transfer, fairly standard procedures for channel flow. And we find that the results are reasonable. Some validation was done with respect to some results here. As you can see here, this is the first part is only to show that the mesh is chosen so that further reduction in the mesh size would not affect the solution. And the second one is a comparison with analytical solution. For the developed case, as you can see, the results match very well. The entrance region, of course, analytical solutions are not available. So we used only the developed one to show that the results are very close. We also did an experiment. We took, this is a plasma etching solution for microchannels. We used, well, these are again rectangular channels with about 100, 150 microns as the thickness, width of the channels, and plasma etching is used. I've shown you some of the steps that are taken, and this is the device that is formed. You have straight channels, U-shaped channels. We did many other channels just to see what the effect would be. We try to optimize it. I'm not going to talk about that here because we have discussed that in the past. But this is the experimentation that was done. And here is the experimental setup. Basically, it's a very simple setup with the flow coming in using one of the smaller, because the flow rates are very small, some impinging flow rates, impingement type pumps are used, and we have flow go through it. We measure the temperature and the pressure. So relatively straightforward, and we compare the results. The outlet temperature is being shown here, and some of the other results are shown here in terms of the pressure. And as you can see, the comparison is fairly good. This was largely to see that the model that we're using, the grid that we're using, and the other approximations that we've made are reasonable, and that the solutions can be treated with accuracy, and the predictability is high. So the model is basically done. And basically what we did was, as I mentioned, one channel, and then we extended into other channels. Each channel has conditions on either side so that symmetric conditions are used, and you can get the entire domain simulated. And then, of course, you have a top and the bottom, and the heat flux coming in, and other boundary conditions that are to be used. So here is the region that we were talking about, and all these points are taken largely to look at hotspots, and you can see how the temperature and the locations, how they vary. We are shown here in terms of the location and where the temperatures are. These are many traverses that are shown here, and you can find out where the highest temperature would be, and that would be a hotspot. Typically, it's at the end of the channel and in one of the corners. That's where the highest temperature appears. If the material has some defect in it, or there are different materials used, the hotspot can be at some other point. But that hotspot is an important issue because we want to keep it below a certain value, typically 80 or 90 degrees centigrade. This is showing pressure, pumping power, and thermal resistance as a function of Reynolds number, which is really dependent on the flow rate. And as you can see, the pressure, if you go to higher and higher Reynolds number, typically the pressure goes up and the pumping power goes up, as you can see from here. As expected, the velocity is higher. You end up a larger pressure drop that is needed to make that flow occur. And of course, the thermal resistance, as you see, higher and higher Reynolds number means higher and higher heat transfer coefficient, and the thermal resistance becomes lower, so the heat transfer becomes larger. So they're very standard and well-expected solutions that you would get with increasing flow and increasing Reynolds number. You will get higher pressure, and you will get lower thermal resistance. Now, you can talk about a pressure limitation, 1.5, 2, or 3 atmospheres, and that would limit the flow rate. And as you can see, these are the cutoffs for different pressures. The reason why we're talking about a pressure cutoff is because you cannot have, obviously, a huge pump just to cool a small chip. So we are thinking about a limiting condition where you can use a reasonable pump to end up cooling the system. And this is cutoff flow rate, which is shown. There is a limitation of 80 on the temperature hotspot and a pressure limit of 2 atmospheres on the pressure. And then you end up with the feasible domain. You obviously cannot go, you can go here if you can go to higher pressures and higher flow rates and so on. But with these limitations, these constraints, that is the feasible domain. And as you can see, the red one is the limitation because of the temperature, and the blue one is because of the pressure. And these limitations are very common, and we are looking at more realistic designs, and that's why we have taken these conditions. Circle and rectangular, there's not that much of a difference. We tried both of them. As you can see, the differences are not very large. This is the hotspot temperature, this is the pressure against the flow rate, and the differences are not very large. So you can, whatever you come up with the rectangular channel, which are obviously much easier to fabricate. Of course, with the 3D printing, you can get essentially any shape that you want, but circular, rectangular obviously look very similar. Then we looked at different substrate materials, and basically bronze and silicon. Silicon, of course, is a much lower conductivity. Bronze is a much higher conductivity. You can see uniform temperature in bronze, and then you can see temperature difference in silicon, and this is in the channel. Similarly here, bronze, the temperature is higher, and when you, like here, you can look at it, the temperature becomes lower. Silicon, the temperature drop is higher. So you can see that this is the silicon, this is the bronze, this is the bulk temperature in terms of temperatures here, and across the channel you see uniformity fair uniformity in a bronze, and you see much larger difference in a silicon. So depending on what material you use, there would be differences. As you can see, delta T silicon, delta T bronze is very small, delta T silicon is much larger. And this is basically looking at different substrate materials in which we have made the microchannels. Whether it's made in silicon, whether it's made in bronze, whether it's made in some other material, it becomes an important consideration because of the temperature and the pressure that you deal with. We also looked at some bifurcation channels, the channel coming in and breaking up into two channels or more. So we looked at that. And again, in this case, most of the temperature effects, as you can see, effects here, and the pressure effects here. Basically, with the bifurcation, you end up with the pressure changing much more dramatically because when you go to bifurcation, the diameter becomes much smaller. Similarly, the temperature effects are seen here with respect to the changing geometry of this. The flow comes in here and then splits and comes in and splits. And because of that, these channels are much lower in width. You have much greater flow rate, much greater velocities, and you obviously have larger pressure drop occurring here, which you see here. And the temperature also shows that instead of going straight like this, the temperature effect is simply because at a lower speed, you end up with higher heat transfer coefficient and you end up with a lower temperature. The mini channels we looked at only to compare. And here's one of the experiments we did in mini channel. We found again that the pressures are really not much of a problem. Pressures are fairly low, and the hotspot temperature obviously increases as you increase the diameter, because then of course the heat transfer coefficient goes down, and as a consequence, the temperature goes up. We looked at some blood vessels, which are basically around the same dimension. Looked at some viscosity models for the blood, and we did some simulation for that because ultimately these are like microchannels. As you can see, they're very similar to microchannels, and the results are also quite similar. This is the pressure along the distance, and again, it depends on what kind of model you use, but the fact does remain that many of these are very narrow microchannels, and the pressure could be very high. We did a lot more work on it. I'm just showing that it can be related to biological applications, particularly flow of fluid through the channels. There's a limitation on pressure, as I mentioned before. You will have, as you go through the volume flow rate, you would cut off because of the pressure drop, and again, you will cut off the pressure, the channel width because of the pressure. There are limitations. Hotspot has similarly limitations, as we mentioned. I had shown this picture before, that depending on the traverse, you find out where the traverse one ends up being the highest point, which is the hotspot. Now, with these in mind, we picked up and did some response surfaces using a simple second order function. We went and did response surfaces. Some of the results are shown here, so you can pick up the optimums point from here. These are responsive for thermal resistance, for pumping power, for pressure, hotspot temperature. So you can try to pick up whatever you like, but obviously each of them would be only one objective function. So if you take a single objective function and your focus is only on pumping power, you end up with an optimum. The red one is the hotspot constraint. The blue one is the constraint because of the pressure. You're changing the flow rate and the number of channels or the width of the channel. And looking at these two variables, these are the two constraints you end up with an optimum point right here. This is a single objective. You can pick out another single objective, which is thermal resistance, and you get very similar situation. You have these two as the constraints, and you end up with the optimum value corresponding here. Most of the optimum appear on the boundaries. Under these conditions, a single objective, you are only maximizing, well, in this case, minimizing the thermal resistance. In the previous case that we were dealing with, minimizing the pressure and so on. Those are the kinds of things that we do, but these are single objective. The main thing is the multi-objective, where you are looking for both the pumping power and the temperature. So you're looking for both circumstances, trying to reduce the temperature, trying to reduce the pumping power. In that case, again, the constraints are the same, but the optimum moves. It moves away from the ends, from the boundaries into a point here. And this is a multi-objective function. And the most important thing is that this solution can be represented best in terms of a Pareto function. Pareto frontier basically gives you pumping power, thermal resistance as a function. It's up to your choice. If you want pumping power to be very high, your thermal resistance is very low. If you want very low thermal resistance, like here, thermal resistance is very low, you need much greater pumping power. If you're willing to live with much higher thermal resistance, your pumping power is lower. So this curve basically is the optimum for a multi-objective function. You can do it with pumping power, thermal resistance, or you can do it with the pressure and temperature, pressure and heat transfer. But this is the main solution that you get out of it. The previous one that I showed, which was this, basically gives you the point, this particular point, but it's only one particular point for certain conditions. Whereas this one is a little bit more general, and you can pick up the right solution. Okay, these are Pareto frontiers for different number of channels. Simply the same kind of result is obtained. As you can see, these are for different cases. Okay, now there is also uncertainty in the heat flux. And I'm showing this uncertainty in terms of the heat flux because when you say the heat flux is 50, it may fluctuate plus minus 5%, plus minus 10% in a normal curve. And that's what is being shown here, that this is the effect of that uncertainty. 5% or 10%, it can change the hotspot temperature, it can change the pressure, because that uncertainty lives with us. We cannot avoid it. It is always there. And without picking up uncertainty, we really don't get the realistic solution. So here is the uncertainty effect that you can see out here. For whatever reason it might be there, but there's an uncertainty. And this is reliability-based design optimization. We're looking at flow and channel width as the parameters. You have a deterministic Pareto front, which is this. Then you have a probability function with respect to 5 and 10. Depending on your probability, if it is 10%, you can see how far it deviates from the Pareto front. So a solution that you are getting here would move here with uncertainty. So without uncertainty, with deterministic, you have a result, but with probability, you get a different result. And that's an important thing. If you want realistic solutions, that's what you need to do. Bring in the uncertainty, find what the probabilities are so that your design is reliability based. This is flow rate and heat flux, very similar case that this is flow rate and heat flux based. And again, this was deterministic, but with uncertainty, the heat flux that you can get, that you can remove, changes, becomes less and less. More and more uncertain the situation is, the lower and lower heat flux you can remove. And that's an important point, that uncertainty is always there. You cannot make it zero. And because of uncertainty, you're not going to get the value that you would have got by deterministic analysis. And that's what is being shown, that the maximum heat flux here, temperature constant, this is all deterministic, as you can see. But when you have reliability cases in there, then of course it will change. But these are the cases. The temperature constraint, you can pick up different pressure case constraints. You'll get limitations of heat flux. You can take different temperature constraint, you get different levels. So these are the maximum heat flux you can get under the constraints, either the temperature constraint or the pressure constraint. You get a limitation on the heat fluxes. But if you add reliability to it, then it will change. I mean, the values will be changed. As you can see here, you get an optimum channel configuration. This is deterministic, the probability. Look at this. The values immediately drop down. And similarly here, as you go to different constraints, the cases change. This is the deterministic circumstance with probability at 3 atmosphere. But if you change the probabilities, the constraints, the values change. Here, you're changing the probability, and you can see that it immediately comes down, that the deterministic and probability will change. So basically, the idea is that if you have uncertainty, the results that you obtain from deterministic analysis do not apply anymore. I mean, the values that the heat flux that you can remove is lower, the pressure that you will have to exert would be higher, and you have to find out that value if you want to get a realistic but reliable design. And that's the whole idea behind this, that you need a reliable design. Let me conclude because I'm running out of time. Microchannel heat sinks have been considered for heat removal and delivery. We did extensive numerical simulation. We validated by analysis and experiment, but it is critical to consider both pressure and heat transfer rate. You just cannot leave it with one. Single optimization is not the best answer. You must optimize the system and operating conditions. There are several objectives which are of interest. Typically pressure and temperature, but others can also be thought of, and there are other constraints that can be brought in. So you need multi-objective optimization, and then you get a Pareto front which will give you a trade-off as the best approach. Response surfaces are good to see what's happening and pick up optimization in some cases, but Pareto front is really the right answer, which will allow you to pick the right solution for yourself, and optimal conditions are chosen for given preferences. Of course, uncertainty will change some of these results, and you have to bring both uncertainty and deterministic cases in your mind. With that, I think I'll stop, and thank you very much for your attention. Thank you.